We're going to take a look at a problem where we're asked to solve a system of nonlinear equations, and the system that we have here has the equations x squared plus y squared equals 5, and also x times y is equal to 2. We can solve this two ways. One is graphically, and then also by algebra. And so I'd like to begin by graphing these equations. So the first equation, x squared plus y squared equals 5, is the equation of a circle with the center at the origin, and the radius is equal to the square root of 5, because we have the standard form x squared plus y squared is equal to r squared, again where r squared would be equal to 5. And we should also get a decimal approximation for the square root of 5, which on a calculator comes out to be about 2.2. So our circle has its center at the origin because x and y don't have any values added or subtracted from them, and we can go about a little more than 2 units in each direction and draw the circle. Next, let's take a look at the equation x times y is equal to 2. And if you're not familiar with this, if we isolate the y, we can say that y then is equal to 2 divided by x, and this is a variation on the reciprocal function. So if we plot a few points here, we can let x equal -2. When x is -2, y is equal to 2 divided by a -2, and that's going to give us a -1. When x is equal to -1, y is equal to 2 over -1, and that gives us -2. When x is 0, 2 divided by 0 is undefined, so we're not able to calculate a value. When x is equal to 1, y is equal to 2 divided by 1, which is just equal to a +2. And finally, when x equals 2, y is equal to 2 over 2, and that's equal to 1. So we can plot a few points here. We have the point -2, -1. We have the point at -1, -2. We have a point at 1, 2. And we have the point at 2, 1. And again, the reciprocal function operates in the first and in the third quadrants. And if we were to plot some fractional values, we would see for x, we would see that the y values would extend upwards. And if we were to plot some higher values of x, we would see that this would get smaller and smaller. So the reciprocal function, or non-standard hyperbola, looks something like this that we see in the purple. We can eyeball the points of intersection, and it looks like those points actually that we plotted at +2, +1, +1, 2, and then -1, -2, and -2, -1. It looks like those are the points of intersection. But we really should test these solutions more explicitly using an algebraic calculation. So when I look at these two equations, x squared plus y squared equals 5 and xy equals 2, two possible solution methods would be elimination and substitution. And in this example, elimination is not practical because I don't have any terms that obviously drop out. This xy term is different than the x squared and the y squared terms of the other equation. So that leaves substitution, and in some equations, if I have an x squared term, I can substitute with another x squared term, or same with a y squared, but in this case I'm not able to because I don't have either an x squared or a y squared term. So I'm going to have to substitute for either x or y by isolating one of the variables. And if I divide both sides by y, I end up with x is equal to 2 divided by y. And I can substitute 2 over y for x, and I'll square that, plus y squared is equal to 5. So when I simplify this squared term, I can see that I've got y squared in the denominator, and I want to get rid of that by multiplying all 3 terms by y squared. So canceling in the first term, we end up with the simplified equation 4 plus, and then y squared times y squared gives us y to the 4th. is equal to 5y squared. And this is a quadratic-like equation. Although it's a fourth power equation, the fourth power is a square of the second power, and then we have a constant. So let's put this in descending order. And we can see now that we have a trinomial which is factorable. So I'm going to factor this and put y squared in the front of each of the binomials. So y squared times y squared gives us y to the fourth. And now we've got factors of 4 that have a sum of 5. We've got negatives here, so factors of 4 are going to be positive 4 and positive 1. And this now allows us to solve not for y, but for y squared. So the first solution, or set of solutions that we get, comes from the factor y squared is equal to positive 4. And from that we can see there are actually two solutions. That y is equal to the positive square root of 4, which is equal to positive 2, or the negative root, which gives us y is equal to negative 2. From the second factor, we get something similar. We get that y squared is equal to positive 1, and from this we also get two solutions. Y is either equal to positive 1 or negative 1. Now these four different values of y are the y coordinates of 4 separate points, but each of those points also has an x coordinate. So we are going to get those solutions. So when y is equal to positive 2, we can go back to this equation here with x isolated and say then that x is equal to 2 divided by y, 2 over 2, which is equal to 1. And so from that first solution we get the ordered pair 1, 2. From the second value of y is equal to negative 2, we can again calculate the x, which is equal to 2 divided by a negative 2, and that's equal to a negative 1. And so that solution is negative 2, negative 1. From our third y value, we had that y was equal to positive 1, and plugging in, x is equal to 2 divided by 1, which is equal to 2. So we have the point 2, 1. And finally, for our fourth solution, letting y equal negative 1, we get that x is 2 over negative 1, which is a negative 2. And so this point is negative 2, negative 1. And as we look over these four solutions here, the point 1, 2 is that intersection point on the graph. The point negative 2, negative 1 is over here on the graph. The point positive 2, 1 is this point here. And the last point, negative 2, negative 1, is also one of the intersection points. So what we find algebraically does verify what we got on the graph.